Hello students, welcome to today's lecture on artificial neural networks. In our previous session, we have discussed about what is a feed-forward neural network, and also we have gone through uh, different types of feed-forward neural networks, starting with single-layer feed-forward neural network and multi-layer feed-forward neural network, and other types also. And we discussed about the differences between the perceptrons and the feed-forward neural networks also in our previous session. And in that discussion, we mentioned that the feed-forward neural networks will be trained using a special algorithm called as a backpropagation algorithm. Okay. So today we will discuss about the backpropagation algorithm for training our feed-forward neural networks. Okay, so we'll start with a simple introduction to backpropagation, and then we'll go through the steps involved in backpropagation algorithm in detail. Okay, so let us start our topic. So here is a simple introduction to backpropagation algorithm. Basically, we know that there are two learning paradigms for training our neural networks. One is supervised learning and other one is unsupervised learning. Where in supervised learning, the target outputs are known uh, at the start of design of our neural network itself. That means the input patterns are labeled input patterns, uh, which can be classified into a special output category. Okay, so therefore, backpropagation is a supervised learning algorithm uh, in which the input data is labeled. Okay, and this algorithm is used for training multi-layer perceptrons, or we can call it as multi-layer feed-forward neural networks. Okay, so why actually we need this algorithm in multi-layer feed-forward neural networks? Why backpropagation? Okay, to understand this, let us go through what happens in training the process of a neural network. Uh, Firstly, we will initialize the weights with some random values uh, of the neural network. That means we'll start with some random weights connecting the neurons of a neural network. Okay. And then by selecting some input pattern or input value, we will try to calculate the output, and we'll compare the actual output produced by the neural network with the target output, or that is desired output. Okay. So if that desired output and actual output produced by the neural network is not same and the error is very huge, then what we need to do is we need to reduce the error such that the neural network performs efficiently for a given input. So how do we reduce this error? To reduce this error, what we do is we need to change the parameters, that is weights of the model, in such a way that the final error term becomes as minimum as possible. So this is the general process to train our neural network. Our ultimate goal will be to minimize that error term in our neural network. Okay, so to achieve this task of minimizing the error term quickly, the possible solution is backpropagation. Okay, so in order to move towards the minimum error while training your neural network, it is always better to use a backpropagation algorithm for training your multi-layer feed-forward neural network. Okay, so that is the reason why we use this backpropagation algorithm in multi-layer feed-forward neural networks. So let us go through the steps involved in this training process of a backpropagation algorithm. In general, so assume that this is our neural network model which we are building. What we do is with the initial weights assigned to the connections between neurons, we will calculate the error term by comparing the response of this model with the desired response of the corresponding inputs. And once this error is minimum, expected minimum, then the model is successful, and we can use that model to make any future predictions by submitting some inputs as model inputs to the corresponding neural network. Otherwise, if the error is not minimum, then what we need to do is we need to update the parameters in such a way that error is minimized, error term is minimized. And once the parameters are updated, again we calculate the error term, and again we will check this error is minimum or not. Okay, so this process, it's a repetitive process. In each epoch, we will perform these tasks. Calculate the error. If the error is minimum, then stop the process of learning or training. Otherwise, update the parameters in some manner by using some specific parameter updation algorithm, and then go back to calculation of error. And this process is called as training process of your model. Okay, so once the training process is successful, we can say that our model is ready to make prediction. Okay, so this is how it works, the training process with the help of back propagation algorithm is done, right? So this is a summarization of the steps involved in the training process of our model. The first step will be calculation of the error to identify how far our model is performing compared with the desired output. Okay, so the model output is compared with the desired output of the model, which will be used for calculating the error term. If it is the minimum error, then we will say that stop the process. The model is ready to uh, uh, apply the specific inputs and calculate the corresponding outputs. Okay, so otherwise, if the error term is not minimum, then what we do is update the parameters. Okay, so if the error is huge, then what we do, we will update the parameters. Parameters are nothing but the weights between the neuron connections and the biases also. And again, we need to check the error, and this process will be repeated until the error term becomes the minimum of the model. Okay, so this process will be repeated until error term becomes minimum. Okay. Once the model is ready to make a prediction, we can use that model to predict the output of the neural network by giving some inputs to the model. Okay, so these are the four steps involved in our training of a feed-forward neural network. And these are the basic steps used with the back propagation algorithm also. Now, what is remained is we need to identify how to calculate the error term in the algorithm. Actually, we need to identify that. And then how do you check that it is minimum, error term is minimum. And then we need to identify a process of updating the parameters. Okay. And you need to identify when to stop this training process. Okay, so if we understand that three things with our back propagation algorithm, then we can use the back propagation algorithm for training our neural networks. Okay. Okay, let us start the actual algorithm. The back propagation algorithm looks for the minimum value of error function in a weight space using a technique called the delta rule, which we discussed in second unit, or a special optimization technique called as gradient descent. Either we can use the basic delta rule, or we can go with an updated gradient descent method for better results. Okay, so the weights that minimize the error function is then considered to be a solution of the learning problem. Okay, that means, so whenever we get some weights that minimizes the error function, that means you cannot go beyond this error. You cannot get anything less than this error. Then we say that the weights which are calculated by the model or the final weights of the neural network. Okay, so let us go through the steps involved in this backpropagation algorithm, which will be used for multi-layer feed-forward neural networks. Okay. So the first step in backpropagation algorithm or any training algorithm will be initialization of the weights to some random values. Okay, so here also we do the same thing, initialize the weights to some small random values, generally between 0 and 1. Okay. And then step 2 is apply a sample input pattern to the neural network along with its target vector. Okay, so for example, if the input vector is x1, x2, so on xn, what we do is we use the target vector, target one, comma, target one, and so on, assuming that there are these many output neurons in the output layer. Okay, so by applying this and this, we will be able to calculate the error term because these are the desired responses from your output neurons, and this is the input pattern we supply to the neural network. With this data, let us begin the actual steps. It actually involves two steps, two passes. One is forward pass, and the second one is backward pass. So in forward pass, backpropagation algorithm calculates the final output of the neurons in the corresponding neural network, starting from the first hidden layer and moving towards the output layer. Calculate the output values produced by each neuron as given below. So the formula is very simple. We will calculate the net output of a particular neuron. Let us say HI is the neuron. Net output from this hidden neuron HI will be calculated as summation of j is equals to 1 to n wj into xj plus p. Okay, for example, if you have a hidden neuron h1, something like this. Okay, so assume that this is h1 and imagine that there are some weights connected to this neuron coming towards this h1. Okay, so let us say it is w1, w2, w3. Okay, so this is w1 and this is w2 and this is w3. Okay, then there may be some bias also. Let us say bias weight is also connected to this neuron. Let us say it is B. So then the net weight is calculated as Wj into Xj. That means if the input pattern is X1 here, okay, and here it is X2, and here it is X3, then the formula for calculating net H1 will be W1 into X1 plus W2 into X2 plus W3 into X3 plus this biased. Okay, so the formula is W1 into X1 plus W2 into X2 plus W3 into X3 plus bias. So that is the formula. So for all the weights connected through the input patterns, okay, for all the input patterns connected to through the weights Wj, you just multiply them. So sum of products of weights and input patterns plus bias term. This will be used as the formula for calculating net output. Okay, and the actual output of the neuron is calculated as out hi. Okay, using a activation function, logistic function or sigmoidal function we call it as, and by sending this net hi calculated in the previous step as a parameter for this sigmoidal function. Okay, sigmoid of net hi is used as the formula to calculate the actual output of a neuron. Okay, the formula goes like this: 1 by 1 plus e power minus net hi. Okay, so these are the formulas for calculating the outputs of neurons, the actual outputs of neurons in hidden layers. Okay, similarly, the output of neurons in the output layer will be calculated using net OI is equals to, assuming that OI is the output neuron I, and the formula goes as the similar to previous one, except that the outputs produced by the hidden layers will be the inputs to the output layer. Okay, so out Hj into Wj plus P. So except this, in place of Xj, we are getting out Hj here. Here Xj is the input pattern directly supplied to the neural network model for calculating the hidden layer neurons output, whereas output neurons output is calculated as out Hj into Wj. What does this mean? Out Hj is the output produced by the hidden neurons, okay, plus bias, okay. So instead of Xj, we are getting out Hj here, right? So once it is calculated, again this net y is sent as parameter to the sigmoidal function, which takes the formula 1 by 1 plus e power minus net y. Okay, so this is how we calculate the outputs of each neuron starting from the input layer to uh, the last layer, that is output layer. Okay, so once the outputs are calculated, then the next target is we need to calculate the error term. We need to calculate the error terms produced by the output neurons. So how do we get it? The error terms is EOI, where OI is output neuron I, EOI is equals to half into target Y minus out Y. Target Y is already known to us, the desired response from output neuron Y, minus this is the actual output produced by the neuron out Y whole square. Okay, so this is the formula for calculating the error term produced by a particular output neuron. Let us say O1. If it is O1, then the formula will be half into target O1 minus out O1 whole square. Similarly, if you have error term, if you have another output neuron O2, then the formula will be half into target O2 minus out O2 whole square, and so on. For every output neuron, we need to calculate the error term using this formula. Okay, and then once every output neuron's error term is calculated using this formula, then we need to calculate the total error generated by our neural network. Okay, so which will be calculated as sum of the error terms produced by all the output neurons. Okay, so EO1 plus EO2 plus so on plus EON, where n is the number of neurons in output layer. So if you have five output neurons in output layer, then the error term will be calculated as E total is equals to E1 plus E2 plus E3 plus E4 plus E5. That is how it will be calculated. Okay. So with this, we have calculated the total error produced by our neural network with respect to a particular input pattern and its corresponding targets. Okay. Now, let us start with the second pass, that is backward pass. It's not phase, it is backward pass. Okay. So what we do with backward pass is we will propagate the error backwards, starting from the output layer and moving towards the input layer, passing through each hidden layer. Okay, so the error term will be propagated backwards, and accordingly the weights will be updated that connects your neurons. Okay, so this process begins at output layer and moves backwards towards the input layer. Okay, in that process we will update every weight that connects your neural network. Now let us see how this can be done, how the weights will be updated, starting with the output layer. So let us imagine that we are updating the weights connected to the output layer. Okay. So suppose Wj is the weight connected to the output layer, some output neuron J. Okay. And then we already calculated the error term caused by this Wj in the previous step. Okay, so the output neuron already uh, produced some error over there. We calculated it, right? With respect to this weight and error term, how do you actually calculate? So just have a look at this diagram. Uh, Imagine the neuron, output neuron here. Let us say it is Y. The output neuron is Y. Okay, this is Y, maybe O1, O2, or so on like that. Okay, so for each output neuron, we will perform this process based on the weights connected. Okay. Suppose Wj is the weight connected to the output neuron OI. Imagine this. Okay, and we know for this output neuron, we already calculated net OI, and also we calculated out OA, and also we calculated this error term produced by this OI. And because for all the output neurons, we calculated this error term, we summed up to get the C total. So we have all this data. Okay. Now to calculate the uh, updation towards Wj with respect to the error produced, what we need to do is, this is the formula, dou E total by dou Wj. We need to calculate this. The meaning is how this error contributes to the updation of Wj. That is the meaning. How this error contributes to the updation of Wj. Dou E total by dou Wj is equals to, the formula goes like this. We need to go one step at a time, starting here. Dou E total by dou out Y. Look at this carefully. Dou E total by dou out Y, and then dou out Y to dou net Y. See this formula. Dou out Y to dou net Y into dou net Y to dou Wj. Okay. So this is how the formula goes. Okay, we calculate dou E total by dou Wj. Once you calculate this, you can use this value to update Wj. Okay, so to update Wj, you need to calculate dou E total by dou Wj using the formula. So you need to remember the formula like this: dou E total by dou out OI, dou out OI by dou net OI, dou net OI by dou Wj. This is the formula, where the first term dou E total by dou out OI is equals to out OI minus target OI. The formula, you can simply remember this formula, which we get by applying the partial differentiation on the E total formula. What is the E total term? It is sum of error terms, and how you calculate error terms? It is using half into target Y minus actual Y. Okay, out Y whole square. So by applying the formula half into uh, target Y minus out Y whole square, by differentiating it with the out Y, you will get this formula, out Y minus target Y. I'll explain this with an example when we go through a solved example later. So as of now, we just try to remember this. Dou E total by dou out Y is equals to out Y minus target Y. And how do you get this dou out Y minus dou net Y? The formula is dou out Y by dou net Y. We know that out Y is the sigmoidal function. Okay, out Y is actually the sigmoidal function applied on net Y. Therefore, you can use this derivative of uh, the sigmoidal function, as I explained in the previous session, as f dash x is equal to f of x into 1 minus f of x. That is the formula for derivative of sigmoidal function. So out y is anyhow a sigmoidal function. Therefore, derivative of sigmoidal function is out y into 1 minus out y. It is similar to f dash f x is equals to f of x into 1 minus f of x, as I explained in the earlier session. Okay, earlier class, you just go through that video to understand how it came. And then dou net y by dou wj will be equal to the coefficient of wj in net y. Okay, so we'll see the net y, and we will see the Wj term by considering the coefficient of Wj in that term. That will be the value of dou net Y by dou Wj. Okay. So don't worry, even if you do not understand this at this level, because anyhow we'll be practicing the problem. A solved example I will explain later. Okay, so when you go through that example, you will definitely understand these formulas. You can write these formulas in your own later. Okay, so don't worry even if you do not understand, but try to remember these formulas because they are helpful while solving the problems. Okay, then okay, now uh, we have calculated that dou E total by dou Wj. Okay. Then for updating the weights connected to hidden neurons, similarly for hidden neurons, this is for output layer. Similarly for hidden neurons also, we use the same process. So this is output neuron, and now we want to calculate the updation of Wi. Later I will explain how W and Wj can be updated. Okay, so as of now, I assume that I just want to calculate the derivative of Wi with respect to the error term for hidden layer Hi. Okay, so I assume this is the hidden neuron with net Hi and out Hi, and I assume that Wi is connected to this neuron. Okay, now how do you calculate to update this Wi? What you need to do is you need to calculate dou E total by dou Wi. This is what you need to calculate, just like we did it in output layer. Dou E total by dou Wj we calculated. Similarly, for calculating the updation of Wi, you need to calculate dou E total by dou Wi. Okay. So how you get formula for this? Again, it is equals to dou E total by dou out Hi, dou out Hi by dou net Hi into dou net Hi by dou Wi. We use the same process to consider the formula. Dou E total by dou Wi is equals to dou E total by dou out Hi. How you get it? Dou E total by dou out Hi into dou out Hi by dou net Hi. How did you get this? Dou out Hi by dou net Hi. Just follow these arrows. Dou out Hi by dou net Hi, and finally into dou net Hi by dou Wi. Okay, so this is how it comes. But this time calculating dou E total by dou out Hi is not similar to calculating this in output layer, because the weight connected to the output neuron contributes error term to that neuron only, whereas since the hidden neuron is connected to every neuron of output layer, the hidden neuron error term depends on the entire error terms of the output neurons. Therefore, dou E total by dou out Hi need to be calculated with respect to every error term of output neurons. So the formula goes like this. Dou E total by dou out Hi is equals to dou E01 by dou out Hi, that is contribution of this error term with respect to Wi, plus dou EO2 by dou out Hi, plus so on, plus dou EON by dou out Hi, where n is the number of output neurons in the corresponding output layer. Okay, so this is the formula. This is an extra term, and now we will consider each one of these. How do you calculate the value of this? Dou EO by dou out Hi. Now the formula is dou EO1 by dou out Hi is equals to dou EO1 by dou out to O1. Okay. Again, you can see the diagram to use this. Instead of using dou E total by dou out O1, we use every term, every error term, dou EO1 by dou out O1 into dou out O1 by dou net O1 into dou net O1 by dou out Hi. Okay, it is like that. For every error term, we will use this formula. If it is dou E01 by dou out Hi, we will use dou E01. Okay, everywhere, and also we will use dou out O1. dou net over. It is with respect to the output neuron over. Similarly, for calculating this value, dou EO2 by dou out HI, what will be the formula? The formula goes like this: dou EO2 by dou out O2 into dou out O2 by dou net O2 into dou net O2 by dou out HI. It goes like that. The formulas, we will calculate everything like this. Once we calculate all these terms, we will sum up all these terms to find the final value of dou E total by dou out HI, which will come over here. Okay. Into what is that second term? Second term is dou out HI by dou net HI. So how do we calculate this dou out HI by dou net HI? It is very simple. So dou out HI by dou net HI is calculated as out HI into 1 minus out HI. Why this formula? The reason is out HI is a sigmoidal function of hidden layer. Anyhow, it is a same activation function used across all the neurons. Therefore, we use the same formula: f dash of x is equal to f of x into 1 minus fx. Okay, so dou out HI by dou net HI is equals to out HI into 1 minus out HI. The formula is same. Okay. And then the last term, dou net HI by dou WI, is calculated as the coefficient of WI in this net HI. Okay, so it's a simple formula to calculate dou net HI by dou WI. Okay, so once we are ready with all these values, we can use this formula to update the weight WI. Okay, so WI is equals to WI minus N into dou E total by dou WI. So where this N, this is not N actually, it is called as eta. Eta into dou E total by, this is the name of this term is eta. Eta represents the learning rate, which will be initialized at the beginning along with the random weights. So eta is constant throughout the training process. Once we select that eta, it will remain same throughout the process. So WI is equals to WI minus eta into dou E total by dou WI. By using this formula, we will update the weight WI. So for each weight in the neural network, we will use the same formula for updation. Okay. For example, for updating WJ, the formula goes WJ is equals to WJ minus eta into dou E total by dou WJ. We must have calculated it before we update the weight. Okay. So what you need to understand here is the calculation of this dou E total by dou WI is not same for the output neurons as well as hidden neurons. Okay. For output neurons, it is a bit easy compared to hidden neurons, where hidden neuron dou E total by dou WI is calculated with every error term associated with the output neurons. That means dou EO1 by dou WI plus so on. So as we saw it in the previous slides, it is a bit difficult to compare to calculating the output of output neurons. So this is the formula: dou EO1 by dou out HI plus dou EO2 by dou out HI and so on. So because of this extra calculation, this hidden neuron calculations becomes tough compared to output neurons. Okay, except that everything else is going to be same. Okay. So anyhow, it will become easier for you once you practice a problem later in our sessions. Okay. So once you practice the problem and you come back to this algorithm and read it again, then you will definitely understand it very clearly. Okay. So and finally, the last step of our algorithm is we need to repeat the steps 2 to 5 until the total mean error of the neural network becomes sufficiently small. You need to understand this point. So when you say that it is sufficiently small, it depends on the corresponding application we are using. That means based on the problem under hand for designing the neural network, this varies. Okay, so there is a simple way to stop your training process based on whether the error is not changed from the previous step or not. So whenever you identify that the error function is not changing compared to the previous iteration, then you can simply stop the process, because even if you repeat the process again, there will be no change in the error function. So in that situation, you can stop training your model. Okay, otherwise you need to continue the process of training your model until the error term becomes sufficiently small. Okay, right. So this is actually not a simple task to perform it manually. Sometimes the neural network model requires thousands of epochs, thousands of iterations to achieve that final satisfactory error function, satisfactory error term, to converge your feed-forward neural network. Okay, so it's not that easy to perform it manually, but while writing the algorithm, we will use these steps. Okay, and apply as many iterations required to converge to the final iteration. Okay, so this is what the back propagation algorithm is. Okay, yeah. So this is about the back propagation algorithm, which will be used in training your multi-layer feed-forward neural network. Let us revise the things that we discussed till now. The back propagation algorithm is required to train our neural network, that is especially for feed-forward neural network, which uses either delta rule and or the gradient descent rule, gradient descent approach for updating the weight values connected to your neural network. Okay, so it uses the back propagation algorithm uses two main passes. One is forward pass, in which we calculate the actual outputs of each neuron in the neural network. When we calculate the outputs of actual outputs of output neurons, because it is a supervised learning algorithm. Backpropagation learning is a supervised learning algorithm. Uh, we also have the target outputs, that is desired outputs, also known at the beginning. So we compare these actual outputs produced by the output neurons of neural network with the desired outputs expected from the neural network, and we calculate the error term of each output neuron in the output layer. Once the error term is calculated, we will sum up all those error terms to find the total error generated by your neural network. Okay, so that is done in your forward pass. Okay, and in backward pass, what we will try to do is we will try to minimize the error function by propagating backwards, starting from the output layer and moving towards the input layer, and updating the weights accordingly in such a way that the final error term will be minimized. Okay, for that we will make use of some partial derivative calculations to update the weights. We have discussed about those formulas which will be used for updating the weights and all. Okay, so uh, once all the weights are updated, again we will calculate the error term using the same process, that is forward pass begin again. In the forward pass, if you identify that there is no change in the error term, then you can stop the process. Otherwise, perform the backward pass again until the neural network converges to the final state. Okay, that means there is no change. There will be no change even if you repeat the same process in the error term. Okay, so that is what our back propagation algorithm is. That's all for today. In our next session, we will discuss a solved example that applies this backpropagation algorithm. We will consider a simple neural network, and then we will see how this backpropagation works. Okay, we'll see that in our next class. Okay, that's all for today. Thank you all for your patient listening. See you again in the next session. Thank you.